Hey guys, welcome to the fifth video. Now in this video, we'll be finally going ahead and making the onboard LED blink on the STM32 nuclear board. So without any further ado, let's get started. So as you can see, I have started the STM32 cube ID. I'm going to just make a new project as explained in the previous video. Okay, let's call this project blink underscore test. Keep all the settings same. Copy only the necessary library files and click on finish. Yes, initialize all the peripherals in default mode. Alright, so here we go. We have our device configurator tool open. Now, as I explained in the previous video, a lot of pins have been already configured for us because that is the default configuration of the nuclear board. So we have UART configured, we have PA5 LED already configured over here, which is the green LED on board, and then we also have a user button configured over here, which is the P1, the blue colored push button. But for this video, we will be focusing on the LD2 green LED button. So a GPIO pin has been already configured for you, but say for example you wanted to configure some other GPIO pin. So how to do that is just do a left click and check if it can be configured as a GPIO input or output or a GPIO analog. And then we go to system core and then we go to GPIO. So as you can see, PA5 has been already configured for us. So let's go through these four configuration options over here. The last one is just the user label. So the first one, as you can see, is GPIO output level, which can be set to low or high. Now this is the initialization value at which your board will be initialized with that particular GPIO. So during initialization, I will set my GPIO output level to low. That means the LED will not glow. Next up is GPIO mode, and I have two options: output push pull and output open drain. Now to understand these two options quite clearly, we will have to go to the reference manual, which I have open over here. And if you go to page number 235 of this particular reference manual, then you have this GPIO output configuration, and this is valid for all the GPIO pins on your STM32 microcontroller. So let us take a snip and only focus on things which are important for us right now. So as you can see, there's an input driver and there's an output driver. So the goal is to control an LED. So basically we'll be using the output driver, and there are more things in this diagram which are not needed, and let's go step by step. So let us cover everything like we did in the previous video. By cover, I mean just hide everything. Okay, so let us also draw an LED over here. So whatever is happening inside this black line is happening inside the microcontroller, and the rest is outside the microcontroller. So we have a resistor and an LED, and that is connected to ground. So on the very left, you have read, write, and read/write. Those are the three things you can do with your GPIO port. So basically your C functions, whatever C functions you will be writing, will be handling these registers, handling or controlling these registers, which is the bit set and reset register, or BSRR, and the output data register, or the ODR. So once again, your C code will be changing the contents of these registers, which in turn will be changing the behavior of your IO pin, and more importantly, your LED. So let's see how we actually go from the software part on the left to the hardware part on the right. So let's uncover the output driver, and then you have the output control block, and then you have some MOSFET configuration over here. And there are two configurations, as we discussed, the push-pull configuration and the open drain configuration. So firstly, let us discuss the push-pull configuration. In this configuration, we will be using both of these MOSFETs, the first one being the PMOS and the NMOS. Pause this video if you don't know how the PMOS and NMOS works, just go ahead and Google it. It's a quite straightforward explanation, not really rocket science. So let's get started. Now, if I set a 1 to this one, which is if I do a GPIO write high or GPIO set on this line, then the PMOS gets activated, which is pulled up to 3.3 volts, which is VDD. And when that happens, the 3.3 volts flows through the MOSFET, through the IO pin, and the LED glows, and then goes to ground. And that's how the circuit is completed. So that is how you actually turn the LED on. Now, what if I want to turn off the LED? I'll write a 0 over here. That will activate the NMOS, and then this particular line will be grounded to 0. So therefore, there will be no voltage and current flowing through the LED. So this is push-pull configuration. Now in the open drain configuration, the PMOS acts as a high impedance. So basically the PMOS can be ignored and is not used. So only the NMOS is used. So what you can do with the NMOS and the open drain configuration is use the IO pin in a different way, where you can actually use an external MOSFET or pull it up to a certain voltage as you require. But for the sake of this example, we'll be only using the push-pull configuration. Moving on, we also have two more options. We can either pull up this particular GPIO line to 3.3 volts with this particular switch, or we can pull it down with this particular switch. We are setting it to no pull up and pull down, which means both these switches will be off. And there is some more protection. So if you have some sort of ESD discharge and some sort of clamping required on the microcontroller, then you have these onboard protection diodes. So that's about it for the hardware architecture explanation of the GPIO. Now let's get back to the device configurator tool. Okay, so if we come back to the device configurator tool, then now we know the exact settings we will have to set the GPIO configuration to. So the GPIO output level, let's set it to low. So during initialization, during the first boot up of your microcontroller, the GPIO will be set to low, so the LED will not be high and it will not be blinking. Next up is the GPIO mode. As we discussed, we'll be going ahead with the output push-pull mode, and then no pull up and pull down, because the configuration will be just directly going through the PMOS and then to the LED. And then the maximum output speed, let's just set it to high. So this is the speed basically at which you are changing the state of your GPIO pin. So how fast can the pin go from a low state to high state and the opposite. Not really important at the moment. This is actually the highest one, and that really depends on the clock speed and the processing speed, and also the speed at which your GPIO board has been configured. And then the last one is just the user label. We will keep the clock configuration same as it was in the previous video. Everything has been set to the maximum value and the maximum clock frequency. Coming back to pinout configuration, let us click on the code generation tool and let it generate the code for this particular settings. Okay, so it has generated the code, and then I'll go to core and then source folder, and then I'll open the main.c file. So on your right, you can see there is an outline tab which lists all the functions that are present in the main.c file. Now I will click on the mx GPIO init function. That helps me jump directly to the function. So the first line of the function, we have declared a structure called GPIO init struct of type GPIO init type def, and then we are initializing the whole structure with 0. Next up is we need to enable the clocks for all the GPIO ports, which is A, B, F, and C. And then we need to set the GPIO output level by calling this GPIO write pin function. This is actually the function which sets a particular pin to a particular value at a particular port. So we have the LD2 pin on the LD2 GPIO port, and we are setting it to 0, which is reset. So we are setting it to low, and this directly corresponds to this value over here. So LD2 pin is actually a hash defined, that's a micro. And if I actually want to see what they have defined, so I can just click on this thing or select this thing and then press F3 on your keyboard. So basically LD2 pin is defined as GPIO pin 5. What port are we using? That's the LD2 GPIO port, but exactly it's the GPIO A port, because that is what we configured over here, as the green LED is on PA5. So that is another hash defined. And then the GPIO pin reset, that is also another value which has been set to 0. The next part of the code is the GPIO pin for the user button B1, which is, well, out of scope of this video, so we'll be discussing this code in the next video. And coming to the most important part, which is the configuration of our LD2 pin. So the init struct has members. So there is this pin member, mode, pull, and speed, which all belong to the GPIO init struct. And let's set the pin to LD2 pin, which has this particular hexadecimal value, which we actually jumped to that particular as defined. And then the mode is set to output push pull as explained, and then we have no pull up or no pull down, and then the speed is set to the highest frequency. You can actually also select this member of this particular structure and click and press F3 on your keyboard, and then you can go to the HAL GPIO.h of your particular microcontroller, and then you can see the description of all these members with some nice commenting over here. Coming back to the main.c file, I'm going to jump to the main function. So the first thing which is done in the main is to initialize all your HAL peripherals, initialize the flash interface and the sysdig. Now sysdig is something which we'll be discussing in the upcoming videos. Next up is we configure the clock of your system. Now, if I want to actually jump to the definition of this function, I can also press F3 and then the ID jumps to the definition. Now, very similar to the MX GPIO init, we have a particular structure of a particular type, and then we initialize with 0. We set the members of the structure with the configured values in the device configurator tool, and if any of these values are not correct, the configuration function will not return a 0, and then it will go in an error handle state. So this is basically a function, and if I press F3 again, I will disable all the interrupts on calling these function, and then my processor will just keep on looping in this while one. So going back to the system config, so this is how I initialize all the RCC oscillators, and then initialize the CPU, AHP and APP clocks with the same structure of the code, just by calling a particular functions and then passing particular configuring structures. And if anything goes wrong, you go to the error handler. Now going back to the main, after the system clock config, we have the MX GPIO init, which we just saw, and then we also initialize UART, but we are not using it. And now we come to the while one, where we do the real magic. So all this part of your code, which is before the while one, will execute only once, and then your processor will keep on executing the code inside the while one. So let us go ahead and blink an LED. For that, I need the HAL GPIO write pin function. You can also find more details about this function by pressing F3, and then it goes to the HAL GPIO.c file where the function has been written. So the function actually needs these 3 parameters. And ST has real nice commenting and documentation about whatever functions they write. So you can also actually copy these functions, and then I can paste the same thing in my while. Now make sure to write your code in between these comments. So user code begin 3 starts here, and then the user code uh, part 3 ends here. So whatever you write in between this comment and this comment will not be rewritten by the code generator. So say for example, if you change some configuration and you generate the code again, this code will stay as it is over here. However, if you write anything outside this comment, that will be erased by the device code generator. So we need to pass a particular port to this function, a particular pin, and then a particular state, which was done exactly over here. So I'm just going to paste the same thing over here and make sure my alignment is correct, and I'll just erase this thing. So basically, before erasing that thing, LD2 GPIO port is basically this value which I have to copy and paste, and then the LD2 pin which goes over here, and then either set it to high or low. So let us erase this thing which we don't need right now. Now the first thing which I want to do is I have to set it to high. So I'll just do GPIO pin set, and if I hover my mouse it says 1. And then after that I have to set a particular delay value, which is done by calling the hard delay function and then passing milliseconds. And then I will copy the same thing, but now I want to turn the LED off. So that's about it. Set it high for 1 second and then set it low for 1 second. I'm just going to go ahead and compile. So here you have all your console output, and here we go. Build finished, 0 errors and 0 warnings. Now, the next thing we need to do before we actually flash the code is to create a debug configuration. And that is done by clicking on this bug icon over here and then going to debug configurations. So I will select an STM32 Cortex-M C++ application and then click on this new launch configuration, which is a page with a plus icon, which creates a new configuration for us with a certain C++ application with this particular ELF file. Now it may happen that this particular field is blank. Now that is because either there are errors in your code and the build did not go through. So make sure there are no errors in your code and the compiler has actually generated this particular ELF file. And you can actually go in search project or browse and look in your folder directory for this particular ELF file. Keep the rest of the settings same, and then we go to the debugger tab. Now there are lots of settings to be changed over here, but the only thing we need to worry about is to select a serial wire debug interface and then select a particular ST link and then scan for it. So this thing actually scans for an ST link on all the connected COM ports, and this is actually the serial ID, the serial number of your ST link, which is actually the ST link on your Nucleo board. You can keep the rest of the settings same, and then click on apply. Now clicking on debug will actually flash the code on your microcontroller. So let's go ahead and click on debug. So it builds the code again, waits for a debugger configuration, and it says download verified successfully. So now let's bring in our Nucleo board and see how it looks. All right, so as you can see on the screen, there's this green line which has been highlighted, and if you can see your Nucleo board, there is this LD1 on the Nucleo side which is blinking red and green. That means the debugger is on and the code has been halted at this particular line 75. This does not mean the hal.init has been initialized or executed. It means the code has particularly halted at line number 75. So the next thing we have to do is press on this green play button, and when that will happen, your CPU will actually start executing all these functions and go ahead and blink these LEDs. So let's go ahead and hit the green play button. There we go. We have hit the green play button, and now you can actually see your green LED over here blinking at a frequency of 1 Hertz, which is 1 second on, 1 second off. Now I can actually stop the debugging by clicking on this red square over here, which is terminate. So that means the debugging has stopped, but the code on your microcontroller keeps on executing. So what we can do with this debugging functionality is we can actually add some nice breakpoints in any part of your code to actually halt the CPU execution before executing that particular line. So let's say we want to halt the code at line 102. So what I do is only do a double click next to the line number, and that sets this blue thing, which is a breakpoint. And I'll also do a breakpoint at line 104. Now what I need to do is click on the debug button again, and that will flash the code again, and now we are halted at hal.init. So now if I click on play or resume, it comes to line 102, because if you can see on the right tab, there is a breakpoint at line 102 and 104. Now if you can see, the code has, this execution has halted at 102, therefore the LED is not glowing. It does not mean that line 102 or the write print function is executing right now. It means it has halted. It will execute when you press this resume button or the play button. So if I press this, after 1 second, the LED started glowing, and then now we are at line 104, and now if I resume again, the LED will go off. And now the LED is off because we need to press resume, so it will go high. So this is how you add breakpoints and go step by step. Very useful feature. I'm going to stop and terminate this thing. Now there is another way which you can actually do blink. For that, I will go to the GPIO C thing, and there is the toggle pin function. So I'll just copy this toggle pin function and I'll paste it over here. Back. Now I only need to pass two values, which is the port over here and the pin, and I'll remove all of this. So what the toggle pin does is basically checks the current state of the LED. So if it's high, it will toggle it to low. If it's low, it will toggle it to high. And then I also need to add our classic delay function and set it to 1000. So here we go. The 4 lines of code now have been minimized to 2 lines of code, and then I can just click on the debug button again, which also builds the code and checks for errors, and then it flashes. So now I will have to remove the breakpoints once again. So actually set a breakpoint over here and then execute. You can see the LED is blinking. So there are 2 ways to blink the LED. So that is about it for this video. We saw there are 2 possible ways to use the code and blink the LED. Now in the next one, we will be playing around with the user button, which is the blue button over here, and learning more about the GPIO input functions. So that's all. Make sure to leave a big thumbs up if this video was helpful to you. See you in the next one.